Okay, so today's topic is actually FIR filters, but since we already have gone through a lot of stuff, let me go through the systems and responses. The signals, actually you will get a lot of exercise on how to create signals, and today or the Spectre stuff also goes through how to analyze it more or less. But okay, so the network is not too fast today. But anyways, let's go through the systems. I kind of try to draw you a say big picture. Just a moment. Mhm. There we go. So that way, good. The big picture. Systems. So we are again talking about linear time invariant systems. And basically, well, we have the system, this black box here, and that black box is actually described by parameters A and B. Mark it as A and B as in MATLAB. Upper half is more or less the what the system looks like in time space, and then we have the same stuff in frequency space. Oops, frequency space. On time space, we have the system coefficients actually, or filter parameters, show up in the difference equation. So we have this AK times Y n minus K equals the sum of BK X n minus K. So they are actually right there, in addition to, well, the block diagram. So we have the, for example, second order system would look like on direct form, looks like this. X input, Y output, and these are the B values, B0, B1, B2, A1 and A2, and A0 is used with almost always 1. Okay, so that would be the second order system. So the same system coefficients on the block diagram, also the same coefficients on the difference equation, and basically then these also describe the whole system. For example, if we have impulse function going in, this what comes out is the impulse response. All right, and on impulse response, you can check basically if you have an nth order system, meaning the highest delay is n. So for example, if this is the highest order delay, and if you have non-zero values after that one, then you know we have IIR system has the non-zero values, after that point, and FIR system has all the values of the highest delay would be zeros. FIR. Good. Lots of stuff already here. Another test vector, what you can do is then, of course, the mu, or basically on MATLAB, if you have these on MATLAB and you want to basically run the signal through the system, then you basically say y equals filter b a x x. That calculates whatever for any arbitrary signal. It calculates the output for linear time invariant system. All right, so that's the times. Almost everything what you need to think about on the time space. So impulse response is the key to find out if it's FIR or IIR. On the frequency domain, let's see, how do I do this one? Okay, in frequency domain, these same parameters actually will appear in h of z in the transfer function. Transfer function is simply the sum of bk times z to minus k divided by ak z to minus k, and there we have the LTI system has a rational polynomial of the z as its the transfer function. Okay, this actually is also the same. The h of z is also the same as z transform of impulse response. Okay. So basically we can get the same stuff also directly from the measured impulse response. Then we can continue from this one and say, okay, what is the frequency response? Frequency response is simply the transfer function evaluated on complex plane at points e to j omega. So we have the angle omega, complex angle omega, and on unit circle we have a point e to j omega. You evaluate the transfer function on unit circle. That's the frequency response of the system. And frequency response actually have two meaningful parts. One is the magnitude response, which is simply the norm of the frequency response, and then it has the phase response. So this is just a representation so that you have the amplitude response. Oops. For low pass filter, let's put a low pass filter here. So we have a poles, for example, here, zeros here. The amplitude response of that one would look like something like this. Quite close actually to this, since the poles are giving gain at that angle. So it flattens the this amplitude response on passband, and then this zero at the unit circle gives you zero response at that point, or that angle, meaning you have the start of the stop band just around there. Okay, so that's the amplitude response typically for low pass filter, what it looks like. The phase response means how the signal is delayed on the system, and this is a delay as a the phase angle of sinusoid. So for example, it could go something like this. Well, not for that filter. Something like that. And then when the stop band, you don't really care. Doesn't care what it looks like. For filters, you always think about what the amplitude and what the phase response would look like for the pass band. Stop band, well, after the good stop band, you shouldn't have any signal after all. But anyways, so that's a typical what a phase response looks like. And then from the phase response, you can also calculate the group delay, meaning, well, this is basically showing the complex angles, but you can also derive the time. So if you take the phase response and derive with the phase the phase angle, what comes out is the group delay, GD. Okay, and group delay basically tells how many seconds or how many samples each different frequency components is delayed on the system. Good. That's almost all. I can still fit a little bit on that one. So the graphical presentation of the zero pole plot. Well, the zero pole plot first of all, what the zero pole plot actually is. Well, it's actually just a different representation of the h of z, meaning that we have the B0 divided by A0, and then we, instead of the sum form, we have the polynomial product form of the transfer function. And there we have the special points, meaning roots of pk are the zeros, and roots of that AK polynomial are the poles. Okay. And those will actually show up as zeros and poles on this plot. Good. How to get these actually? You would use the same A and B, but just say roots of polynomial defined by B. And the same thing here is the roots of polynomial defined by vector A. Okay. That's how you do it on MATLAB. This plot you can get from MATLAB saying z-plane. And frequency response, you get saying Frich in MATLAB. And again, same B's and A's are showing up everywhere. And that was the was it GRP delay? I'm losing the blue point pen. So this is GRP delay. And again, the same values or same system coefficients B and A also there. Okay. So fundamentally, it's everything goes around these system coefficients. This far, what we have been doing is just the analysis of the system. So system coefficients have been given. What is filter design all about? It's basically the reverse process. We start from desired frequency response and then go to the system parameters, and then we can analyze it otherwise. Same tools are still used. Okay, over and over and over again. Excellent. So, any questions about the what we have been doing this far? Good. All right. Okay. So, where am I? Oh, is my mouse there? Okay, not systems. We are going through the FIR filters today. As soon as the network starts working again. Okay, there we go. The DSP theory filters 1. That's the topic. So, FIR filter design, and basically some fundamentals. You already should be aware of these, basically. So we have divided. Generally, the filters are divided by their spectral response. There's a low-pass filter, probably the most common filter of all of those. Band-pass filter, band-stop filter, high-pass filter, and then this multi-band filter, meaning more or less like a fixed equalizer. Then digital filters are categorized also as FIR filters and IIR. So they are also characterized by the there's impulse response. Those are the most important parameters when you start designing a filter. You should, first of all, well, this is for the low pass filter. You should define the pass band. What is where the information actually is. That information about that one comes from the signal spectral analysis. So you need to recognize what part is signal, what part is noise. I already cleared everything, but anyways, for example, on the spectrogram, what we had there, we had a 440 hertz signal, and then we have also that 3 times that 1320 hertz signal. Yes, 1320 hertz signal, and that's the information, and you probably would like to keep that information on the passband. Okay, that basically defines the lowest possible minus 3 dB point. Why minus 3 dB point? Well, for historical reasons, that would be the point where the amplitude response have been going down by 3 dB, meaning half the signal power is left at that point. Then the stop band. Stop band attenuation is another parameter. Where is your noise? So, and how much you need to suppress the noise. Okay, depending on what is your information requirement, where is your information and where is your noise, basically that defines the point of basically that one. So you need to define 2 points. One is the point for the 3 dB point. Another one is where your stop band, where it starts. and how much attenuation is needed. So I will draw you a picture. So for signal or the filter design, you need to decide a box like this. That point is the passband corner point, meaning what is your cutoff frequency, and basically also how much of attenuation variation you can tolerate on the passband. So that's also it's called to ripple. How many dB of ripple you can tolerate on passband. Another point you need to decide is that one, which is the how much. Oh, okay, that's the stop and start frequency, and basically how much attenuation you need for this filter. So this is the usually the 0 dB level. That one is the required attenuation A at that point. Okay. Just notice basically something here. First of all, the ripple. If you're using, for example, analog filter called Butterworth, it has a flat passband. The passband may be flat, and that will be the 3 dB point there. Or it can be also, say, some of the Chebyshev type of filters. So you may have this kind of behavior. This is not necessarily anymore the 3 dB point, but the ripple amount. So 2 dB is quite often used for Chebyshev type filters, the passband ripple, and that also defines that corner frequency. It's not always 3 dB automatically. It depends on the filter type. Okay, another thing, think of all the filters that actually would fit into this point. Any of those will do. Or if you have a filter like that, it also defines different boxes. So that is also, if you take this one, then for example, it also defines this kind of box where you have the stop and start frequency here and less the attenuation. And all of this actually comes from the from your filtering requirement. How to match that point and that point. Okay, but anyways, passband, corner frequency, amount of ripple here, stop band, corner frequency, and how much attenuation is required. Good. This transition band here, it's just the frequency range from the passband corner to stop band corner. All right, so high pass filters, the same thing, but you know the numbers are just opposite. Band pass, okay. Band pass actually has two passband corner frequencies and two stop bands. The stop bands don't need to be necessarily symmetric, but they can be totally different. So depending again from the application, how much you have attenuation requirement for each of the bands. Band stop, okay. Band stop has this common stop band, two frequencies there, and then it has a pass, the kind of low pass section which has a corner frequency and ripple, and again the high pass section which may also have different ripple requirements than the low pass. So again, these don't need to be exactly the same. I was just lazy making the picture. Okay. Yeah. The passband ripple, as I told you earlier, that's basically just variation of passband amplitude response. On analog filters, especially the Chebyshev type, that has a variable ripple. Good. Then a couple of words about, so these actually, the earlier was general for any filter, FIR, IIR, analog or digital. But then about the FIR, couple of reasons why to use FIR filter. One very good reason would be actually FIR filter is always stable. You cannot oscillate with FIR. Most of the time, FIR systems are also kind of, well, depending of course your implementation, but sometimes you get funny values from A to D converter. It might actually give you overflow values, FFFF, as well. That's usually used for overflow only. That kind of values. But this can actually recover from the overflow. IIR filter, it uses previous values. If you have a not on number, meaning some overflow on those previous values, then basically the rest of the values out of that filter are also the not the numbers. Okay. But FIR filter always stable, and you can easily have the linear phase response out of that one. And they're basically giving you only three methods, or mentioning three methods of designing. One is the kind of impulse response truncation, which is really only for one reason only here. It's because of the educational reasons. So the basically the truncation means that you can, in principle, measure the impulse response of any system by feeding in a step function, for example. Well, step function in continuous time goes into a continuous time system. Then you basically take a digital sampling oscilloscope or other sampling system, sample hold, A to D converter, and basically this one is giving you mu, well, not mu, the step response of the system in digital domain. So you have digitized the system here. Analog system, any system, feed in the step function and then sample the output. You will get step response, which is basically exactly the same as impulse response minus previous impulse response. No, not that way. From the step function, you get into the impulse response simply by first order difference. And how to do the first order difference? Well, this is, think of the system which has the y of n equals just x of n minus x of n minus 1 in MATLAB. In MATLAB, this one has the AA equals 1, 0, BB equals 1 minus 1. Now you can make a basically calculate a system impulse response. You measure the step response run square wave through a system, and then just pick one of those, all integrate over multiple steps, and what comes out, you will actually get the impulse response. But at the same time, you need to truncate it. All the natural systems are IIR systems. Okay. With the sampling, you should sample infinite time to get exact impulse response, but you basically just say take few thousand values until this part goes around, say, this least significant bit level. Then it's enough. Now you actually have truncated the impulse response. It's close approximation, but it has some effects due to the analog system representation in digital domain. Analog system always have infinite frequency range. In digital systems, you have just from 0 to sampling rate and sampling rate over 2. And depending on your aliasing filter here, you might have nasty artifacts like the Gibbs effect, meaning the aliasing effect of the stuff. But anyways, that's one place to start. And yeah, I have done something very simple here. RC low pass filter, and that's my lab setup. I have the function generator, digital sampling oscilloscope, and okay, that's the step function, which is not optimal. As you can see, it's not really a step. It has some artifacts on it already. That's the step function. I took that data to MATLAB, calculated the impulse response, did Fourier transformation, meaning I did the spectrum of the impulse response, which is actually the amplitude response. Okay, and that's the difference. So it actually comes out pretty fine, except that on the highest frequencies, I hit the noise floor before it starts popping up. But even on the optimal case, without noise, you will get this one going up, while the analog, of course, goes into infinity and beyond. Okay, so that's the even on optimal case, higher frequency, this method always fails. Okay, but anyhow, it's one way of thinking. Okay, it's the impulse response, and actually the frequency response is nothing more than just the Fourier transformation of impulse response. Good. Windowing method is a nice way actually to think about it other way around. Okay, now we are starting from the spectral phase. So the thinking of the whole idea of creating a filter. We start with the box. Well, we started from the signal analysis actually. So signal spectrum, we have the information and then the noise. Information should be within the passband, and then you should reduce as much noise as possible. That's the simple thing. Okay. So, but anyways, think of what that we would have the cutoff frequency fixed, and then we have also the stop band start frequency fixed. We have ripple fixed. We have also the stop band attenuation fixed. Where this continue? Well, we can start by so-called windowing method and think, okay, wait, this is a spectrum. If we can do a spectrum by Fourier analysis, how about we also have the inverse Fourier transform? Maybe we could do something about that one. Yes, we actually do the not inverse Fourier transform, but inverse Laplace transform. Say, so we start from ideal continuous time low pass filter, even if you are designing for something else, for the reasons I will show you later. But anyways, we start from ideal continuous low pass filter, meaning the frequency range goes from -infinity to infinity, and then we at the middle around 0 we have these cutoff frequencies. This will be ideal. Passband is totally flat. The amplitude response 1, and then also stopband is totally flat, so it filters out everything beyond the 0.5 normalized frequency. Okay, we do the inverse Laplace transform, which appears to be a inverse Laplace transform of a box, rectangular box. And what comes out is a sinc function, sine xt divided by xt. You should remember that one from some mathematics course, probably. You have done the Fourier transforms and Laplace transforms, I think. Usually it's on the first year spring semester math course. Yeah, or second year beginning engineering math. Okay, and sampling, if we put some real sampling rate, then basically that thing comes as a, okay, 2 times the corner frequency divided by the sampling rate, meaning the corner frequency divided by Nyquist rate. Okay, that's a scaling factor for this scaling factor for unity gain system. And then inside of sinc, you have the n, which is index, and then we have the same factor there. So basically, you just have that corner frequency divided by Nyquist rate as a multiplier, and then also multiplier by of n. Okay, and it looks like that. All right, so practically, this one is mathematics, and it says that if we had numbers from -infinity to infinity, then this would reproduce that perfect box. But life is not that easy. Mathematically, we need to truncate this the impulse response again. Yeah, the impulse response. That sinc is actually now the impulse response. So it answers the questions: what is the impulse response of the filter which has that box? We started from the box. Inverse Laplace transform of that box is the impulse response. So the box is actually the transfer function, and the impulse response is the inverse Laplace transform of transfer function. Okay, and this is when we do FIR, finite impulse response system. In order to actually use that sinc, we need to cut the number of calculations, and we cut it by mathematically multiplying with a box. So practically, this windowed sinc then is impulse response of a system with a cutoff frequency of the what we define, but the truncations does something for it, the box itself. So this is extra. This we need for calculations. We do not have time from minus infinity to infinity. It would take more than lifetime. Right, so now we do the analysis of this one. Okay, we have the design, we got okay, well, let me take another page here. We started from the design. We say, okay, this is our h of z looks like that. Okay, from that we got h of n. So this is frequency space, this is time space, which is sync, but we cut it somewhere, okay? And now we do the analysis of this one, what kind of frequency response it would have. This would be optimal, but we did something for it, it's not. We have the sync, which will produce exactly the box. Okay, but then we also are multiplying with this one with the box. Box shows up in frequency space as sync. So box, Fourier transform of box is sync, and well, also inverse Fourier transformation is also of the box in time space is a sync. Okay, that's a sync. And then we have the multiplication in time space. Same thing as for which is actually the whole idea of filtering is multiplying the signal spectrum with the system amplitude spectrum to get rid of the unwanted frequencies, which is same as convolution in time space. The same way multiplication in time space is convolution in frequency space, meaning that this sync actually will be convoluting our nice, beautiful box, and you will get an envelope like that. And all of that stuff here is extra compared to our design. All right, math, and that's basically what came out. That's absolute value. I put the signals, just also going in the negative terms. So, yep, and well, let's see. This one is in linear scale. Now we have magnitude in logarithmic scale. So we have the cutoff frequency is covered by setting up the cutoff frequency of the box, which sets up the form of sync. However, we have plenty of stop band ripple. Stop band is ugly. That first point there is actually just 20 dB. Okay, what we can do actually, we can take a smoother window shape to reduce the amount of high spectral components on our spectrum. So basically okay, that box shape here will be, when you do the Fourier transform or Laplace transform, you will get sync if it's rectangular box. But if you reduce the amount of high spectrum components, what happens is basically you get better attenuation in exchange of longer transition bandwidth. So when you smooth the edge, you get transition bandwidth higher, but you also get more attenuation. Since you have less high spectral components on this smooth box than in this hard box. All right. So few window shapes. Rectangular gives stopband attenuations about only 20 dB. Bartlett, meaning triangular window, is already giving more stopband attenuation. Hanning window is half cycle symmetrically biased cosine. So half cycle meaning, well, that part and another part here. And that gives you, you know, quite a lot of more stopband attenuation. Hamming, okay, half cycle but asymmetrically biased cosine gives you about 60 dB. Blackman is my favorite, half cycle cosine and full cycle harmonic. Okay, and they look more or less like that. So box is the blue one. Okay, go from here to there, and well, 0 on both sides. But because of there's 0, we are not taking those into account. And those are the spectra. Okay, more attenuation, better the filter is. You also see that this transition band is also changing from the box. Box basically has a good transition band, but okay, stopband attenuation is poor. Then basically going to the Blackman, which is here. Okay, you got about 3 or 4 times wider transition bandwidth, but then your stopband attenuation is around 70, 80 dB. It's already quite nice. Okay, now the last part is how to fix the transition bandwidth. So what we have currently is we have the control on cutoff frequency. That defines basically the the sync part. So we have the cutoff frequency divided by Nyquist frequency times sync of n times Fc divided by Fn. Well, Fn is the Nyquist frequency, Fs over 2. Okay, so we have the cutoff frequency covered. Then we have another one was the we can adjust this window shape, smoother window. That basically gives you better stop band attenuation. Third one, we still need to fix the transition bandwidth. That comes from a nice mathematical fact that if you multiply time, you actually are doing also division of frequency. So longer sample, meaning wider window, gives you better spectral resolution, meaning you squeeze the transition bandwidth. Wider window gives narrower transition bandwidth. Okay. Those are the parameters what we need to fix in order to match your magic box required. 3 dB stopband attenuation, and then the transition bandwidth. So one window shape actually gives the that one here, and wider window, narrower bandwidth, transition bandwidth, that affects that one. Okay, good. Now we can go and take a look what it really how the filters would look like. But before that one, some transformations. That was low pass filter. How about band pass? All right, easy. By modulation, old-fashioned amplitude modulation. You have probably done this already on radio technology or something like that. If you have a signal spectrum somewhere here, if you want to actually move it somewhere other place for radio transmission, you have the modulating frequency, and you just multiply or mix the signal with the modulating frequency, and you basically get half of the band here, another half on the minus FM. Okay, frequency modulation. But anyways, this is mathematics. So whatever the frequency is, the spectrum is, it transfers that one into another place, even for sampled systems. So frequency shift is same as amplitude modulation. And if you have a low pass filter with, all right, maybe I should actually draw this one over again. So low pass filter, just make it a little bit more clear. Okay, low pass filter, cutoff frequency here, FC, and then we have a modulation frequency somewhere here. What happens, we are actually transferring that one in here and the other part in here. So negative frequencies. So the bandwidth is actually 2 times the original cutoff frequency of the low pass filter. But otherwise, it inherits all the nice properties what the original design had. On the other hand, magnitude is scaled by half. So basically, you get 3 dB attenuation on that one because of splitting the spectrum, splitting that one into plus and minus parts. So what you need to do when you are doing the modulation or amplitude modulation, you're actually losing some power. Half of the signal power goes to the modulation. It's lost, but you can just multiply by 2 the amplitude, then you get back to the normalized. Yeah, so that filter modulated, yeah, it's right there. Band pass. High pass, even easier. Think of the modulation frequency same as the Nyquist frequency. You are modulating the low pass filter directly to the high pass filter. Okay, remember when you are putting the cutoff frequency here, this one becomes the bandwidth of the high pass filter, meaning that it's not the cutoff frequency. So 100 Hertz cutoff frequency for this low pass filter, and now I had 1000 Hertz sampling rate. Nyquist rate is 500 Hertz. This is bandwidth is 100 Hertz. So the cutoff frequency of high pass filter is 400 Hertz. So when you are designing a high pass filter, you will start from low pass filter with a cutoff frequency is the same as the high pass filter bandwidth. Okay. Another thing. Yeah, nothing. This already shows you something that how to design a bandstop filter. You design low pass filter, then you design high pass filter, then you add them. Add them together. So yes. So these are linear systems. So if you have linear system, two parallel linear systems, H1Z, H2Z, basically those are linear, meaning that the full system transfer function is simply sum of the transfer functions, which means that, well, you can basically add the impulse responses. Just add the impulse responses, you would basically get a single system with desired properties. One small detail here, stop band attenuation. You can actually double, depending on your filter design, basically, if these points here, the highest points on the stop band are actually on the same place, you are adding the stop bands together, meaning that you're losing attenuation on stop band. So you need to have some error margin there. Okay, so summary of the window width method. Select cutoff frequency of low pass filter, select window shape, adjust window width, transform if necessary. Good. Wow. Let's have a 5-minute break, since this was heavy stuff again, and then we will continue with the with this MATLAB exercise.